Welcome to more stories of the Secret City, an Oracle class on June the 24th, 2024. I have my special guest with me today, Cameron Reed, and he's going to be talking to us about a book that he's produced, the Manhattan Project Encyclopedia. After his presentation, we'll have some time to talk about our upcoming series in the fall and what you would like for me to include there. So be thinking about that, but also pay attention to what Cameron's going to do. And then at the end, we'll wrap up by talking about the next session. Cameron, we're really glad to have you here with us. I've not gone into details about introducing you, so if you'd like to say something more about yourself, feel free to do that. Or go ahead and begin, and then begin your presentation.
Okay, well, it's not going to be a terribly formal presentation, but hi, everybody. I can't see you. I think I got something set up incorrectly here, but it's nice to see you, at least electronically.
I-
Um,
I'll be watching for the chat if anyone wants to put anything in there. And again, if you just unmute yourself, uh, Cameron will hear you whether he can see you or not, and he will let you ask any questions you want to while he's doing this. Okay, Cameron, go ahead.
oh, okay. Well, I'm a little bit of background on myself. Originally, I'm from Toronto, Canada. Um, I lived in Michigan for 25 years, as you can see, I hope, on your screen here. Now retired. I had a good career there of a quarter century at Alma College in central Michigan. And a few years ago, my wife and I moved back to Nova Scotia, where we are now, and that's where we originally met. And so I'm keeping busy in retirement is just a synonym for just as busy but less money.
I know.
And so keeping busy with some publication projects and teaching some classes part-time at local universities. And I have another part-time gig as an editor with a physics journal. So it keeps me out of trouble. Anyway, over the years, I guess as a physicist, I began life as an astronomer. But I think you can't help be interested in the Manhattan Project if you're a physicist. It's just so compelling, as I'm sure you all know. And so many years ago, it all began innocently. Um, Probably a good 35 years ago now, I read Richard Rhodes's book on the making of the atomic bomb, and I just found it captivating, and I wanted to learn more about how did the physics of the Manhattan Project work, how did these uranium separation techniques work, and it just kind of went from there. And and I found it was just a bottomless rabbit hole of fascinating physics and organization and personalities, and of course the context of the times. So I ended up publishing a number of papers in basically physics education journals, because a lot of it can be, with some background, presented to a class of undergraduate physics students. And so I ended up publishing a number of papers and some books on the history and physics of the Manhattan Project. So that's been going on for, oh, probably about 20 years now. Um, and as I began to gather this information, it became a little overwhelming. Um, of course, there's so many aspects to it that I ended up with so many books and papers and documents, and it was beginning to get a little out of control. And a few years ago, I thought I got to a point where I was wondering, I would remember something and I would think, oh, wait a minute, where did I get that factoid, or who said that, or who published that, or whatever. And Sorry, did somebody say something?
Richard, you need to mute yourself.
Excuse me. So I thought I've really got to gather information together here in some coherent way, and I began just initially for my own sort of internal reference, just building up a document which in the back of my mind I was thinking of as a Manhattan Project encyclopedia. And the idea was it would be an alphabetical list of entries, like a regular encyclopedia, but it would give sort of capsule entries on people, places, devices, physical concepts, uh, you know, locations, events, all the personalities involved in the development of the Manhattan Project. So this began to come together, and a couple of years ago, I thought, well, maybe this would be something that other people might find useful. And other books I had published with the German publishing company Springer. So I approached them with the idea, and they went for it. And in fact, Ray, uh, I hope later today to submit the manuscript to Springer, but I was holding off in case you had any last minute suggestions uh,
Okay, good.
from the version I'd sent you a couple weeks ago.
Um,
Um, but anyway, it's pretty well ready to go as a consequence. And the beauty of so much modern computer software is that, of course, you can jump around electronically. So if I can just take the liberty of kind of describing what I've done here, I'll kind of scroll through the current version. So there's the usual preface with acknowledgments and whatnot, and some primary sources on the Manhattan Project, which of course is almost endless. If you Google it, you're going to get millions of hits. And Ray, you get an acknowledgement down here. There you are.
yes,
Okay.
thank you. And
Um,
I will give you a final input uh,
okay.
sometime probably very late today, but I'll get something to you.
Oh, that would be great. Okay. And an interesting aspect of this is that you come into contact with some very interesting people who have dug into sometimes some very detailed aspect of the Manhattan Project, and it's just sort of fascinating. So, excuse me. This is divvied into 3 chapters, and the first one is 10 pages or so, and it provides a very condensed overview of the Manhattan Project, starting with the idea of atoms and isotopes. But the premise is that readers are, I hope, going to come to it with some idea of what was going on. But it gives a survey of some of the history of uh, the development of atomic and nuclear physics in the early 20th century, notation for isotopes, and then to how fission came to be discovered in late 1938, and the prospect of a chain reaction emerged pretty quickly with a nice cartoon of a fissioning nucleus. And as I scroll through this, you will see that some things are highlighted in red boxes. And wherever there's a red box, whoops, it's an electronic hot link. This one doesn't go very far. But it allows me later on in the encyclopedia proper to do basically a limitless amount of cross-referencing, which is very handy. And so a reader with the electronic version can scoot around between entries in a very convenient way, as opposed to physically flipping pages. So we get to the discovery of fission and some of the intricacies of that, and how they came to realize by, in the last paragraph here, about mid-1940, the distinction between reactors, as you have at Oak Ridge, had at Oak Ridge with X-10, and of course out in Hanford, the different possibilities for reactors and bombs, and how these things might function. And so some of the background to that, with the reactor end going to plutonium, excuse me, I've got a summer cold here. The idea of using a controlled reaction to breed plutonium as a parallel process for making a fissile element, and the realization that by late 1941, it'd be pretty well established that there would be two possible routes to nuclear weapons, using uranium-235 by directly isolating it, as you did with calutrons and the K-25 diffusion plant, to isolate the explosive isotope of uranium, and in parallel to develop reactors to breed plutonium. And of course, the directors of the Manhattan Project making the decision to pursue both possibilities, because they didn't really know in advance what might turn out to work and what mightn't. And then some description of how the administration of the project got set up, with the Manhattan District under General Groves here in mid-1942, and Groves choosing Oppenheimer to run the Los Alamos laboratory to actually design and ultimately build the weapons used at Hiroshima and Nagasaki. So a location map of the predominant locations around the US where the work took place. And I guess I really should have added Canada here, because there was some activity in Montreal with reactor development, and out in British Columbia as a source of heavy water.
I agree that that would be good to add, and also Dayton, Ohio.
Oh, that's right. Okay, let me write this down.
Yes, please do that.
You know, that's nobody's ever pointed that out. Dayton,
Mhm.
Ohio, where the polonium
Right.
was isolated from slugs of bismuth exposed in the Hanford reactors to isolate polonium for constructing initiators,
Yeah.
neutron initiators for the bombs. Okay,
How about in California, the radiation laboratory
I
at
guess I could
Berkeley?
have Berkeley there as well.
Okay.
Okay. Okay, obviously they're not going to get the manuscript today. That's all right.
That's okay. I may
Yeah.
need another couple of days if you'll allow me
Oh,
to
yeah. Hmm.
do it anyway. So if we could say, let's try to do this by the end of next week, would that be all right?
Okay, yeah, I'll just let my editor know that, and that'll I can be working on these other things in the meantime.
Okay, very good.
Um,
And class, if you have any observations, please speak up. Now's a good time to get input for camera.
Absolutely. Um, and of course, today is going to be the day that the Stanley Cup returns to Canada. So,
Yeah.
uh, in any event, hope springs eternal. Um, okay. And then this opening chapter moves on to the Little Boy and Fat Man weapons and the Trinity test, and Hiroshima and Nagasaki, and a little flow chart of how all of this went. Some of the details of the Little Boy and Fat Man bombs, a schematic cartoon of how you could arrange a Little Boy gun type fission weapon. And this was thought of early on. This concept was certainly floating around at the start of the work at Los Alamos as a possible way of assembling a critical mass when they came to have enough U-235. And there's some discussion of why the Fat Man design was different and having to use implosion. Excuse me. And then on to the Trinity test, of which there was one color photograph taken. One of the Los Alamos photographers set up one camera to record a color image. And that's a kind of classic that's reproduced here. And so we have the little boy and Fat Man bombs. So there's this roughly about a 10-page introduction. As I think of it as a kind of a Reader's Digest condensed version of the Manhattan Project. But then the work, which is in manuscript form, is I think I got about 280 pages here at present. Okay. And then it delves into the encyclopedia proper, and it goes numerically, but for a few numerical entries at the beginning, such as using 25 as a code term for uranium-235. And then you begin to see all these nice red linkages. So if, for example, I click on the link for Trinity, it will scoot me down a couple hundred pages to the Trinity entry. Now, I don't think I can get back to, I guess I could use the...
I'll give you a thought. You can put a link that says back to the top. You might place that periodically through there and just go back to the
Yeah,
very,
that would be a little awkward, but let me
yeah,
write that down as an idea.
yeah. And you might just do it at chapter headings or at some point at the
Yeah.
end of the chapter, give us a choice of it going back to the beginning of the encyclopedia
Hmm.
or,
Yeah.
or back to the front of the book, you
Or
know.
do it, yeah, do it periodically or
Oh,
something.
yeah, and the other thing would be a list of chapters somewhere
Well, it
that links back, you know.
I think they'll have that in the printed version. It turns out there's only 3.
I
Uh,
got it, got it. Okay.
yeah. Anyway, that's something I will certainly be
Okay.
thinking about. So let's see now. Where was I? I'm scrolling through a PDF here, and I'm surprised there's not a backwards arrow. Sometimes Acrobat does things I don't understand.
I agree. And I don't see any way for you to get there other than to scroll.
Yeah. Um, but anyway, you get the idea then that you can scroll around to different, this software, which is, some of you may be familiar with a mathematical typesetting program called TeX. And it's a little opaque when you begin to learn it, but then you realize it becomes extremely powerful, and has all of these cross-linking functions where I can set up essentially as many cross-links as I would desire, and to any item that I would desire. And so I could flip from Trinity to Oppenheimer. And so you get the idea, and you can scoot around almost endlessly and bring us back near the top to Vannevar Bush. And
What I was going to suggest is pick one that you know is early on in the book.
yeah. So he's well, he's up at page 49. So whoops. But let me kind of scroll roughly back to the top here. And of course, I ended up with about 300 entries. It was hard to know, to some extent, where do you cut this off? How far down the chain of people that were involved do you go? And because it could be practically endless. But so I tried to get most of the, I guess what you would call major personalities. Although that's, and I got a lot of good feedback from sending advance copies of my list of proposed topics to various folks, and just getting feedback on, who do you think I should include, or have I missed something important? And I got a lot of good feedback that really helped flush things out. So there are some in.
Cameron, this is Paul Taylor.
Hi.
One way to easily go up and down is you can move your cursor over to the little dividing line between the main section and the right section over to the right. You'll see
Yeah.
that will move up a little bit, that little button. If you
Yeah.
click on that, you can zip up and down as much as you want.
Whoops.
There.
There we go. Yeah. Yeah, I knew that was there. Boy, this is strange, isn't it? But anyway, just think I pay a subscription to Acrobat just so they can confuse me. Okay, so there's some things it does stray a little bit in that I thought, well, I can't totally divorce the Manhattan Project, say, from some of the activities going on, particularly in Germany. So you would find a connection, say here. So I don't have a link under the ALSOS mission to the German B8 reactor. In any event, so there's a few things that you would find.
That would be a good one to add.
Yeah.
And people are going to want to know about that German involvement.
Oh, yes. I'm just making notes here.
Mm.
That'll be easy to slip in. So people like Heisenberg show up, obviously, Otto Hahn, some of the main characters in the German program, the ALSOS mission with people like Sam Goudsmit and Colonel Pash and whatnot. So I tried to get kind of reasonably complete without going overboard, I guess you could say. And there's over 100 images, ultimately, maps and line drawings and photographs to help give it some visual appeal as well. And you learn all kinds of curious things when going into this, like the various code names that they use for different uranium compounds that were used in the processing at places like Oak Ridge. And I've tried to be, and I'm kind of prattling on here, I realize. I've tried to give readers references so that they can dig into topics in more detail if they want more detail and be practical to have here. And the green boxes above my cursor here, anything in a green with a number will take you to a master reference list down near the end of the volume. And there's what have we got? I think I got about 275 references. Okay. So these are to other books, documents, journal publications, government documents that are, I think, credible sources of information, because of course you can find a lot of kind of nutty stuff out there about the Manhattan Project. So I've tried to give a pretty comprehensive bibliography of references as well. Definitions of some technical terms like becquerels, if maybe a journalist comes across some story about radioactivity and needs to know what a becquerel means. So there's both qualitative and quantitative material in here. And it goes largely from, well, A to Z. Oh, there was Enrico Fermi. Okay. And I love some of these photographs. I love this one in particular because there's Enrico Fermi holding his trusty slide rule. And I still show my students a slide rule to show them how I'm such an ancient, I guess I'm such an ancient guy. I used a slide rule in my first year of university because calculators were just becoming affordable then. And of course, the students have never seen anything like this. And I recently showing a slide rule to some students, and one of them gasped and said, "You mean you did exams like this?" Yep. Whole generations of people did exams like this. Any event, there we have Enrico Fermi and Richard Feynman, and a fairly extensive entry on the process of fission, and some of the people involved, the concept of the fission barrier, and so on and so forth. So if there's anything anybody wants to think of a topic off their top of their head, I'd be happy to see if I've got it in here. Ray, you had suggested last time we spoke tubaloi.
Yes.
Let's see, it's got to be under the T's, SEDs, of which there was lots at Oak Ridge.
Can you can search this?
Yeah.
Can you not? There you go. There you go. Quicker than
That's kind of stupid, isn't it? All right.
oh
Also,
no, don't worry about it. That happens to all of us more frequently as we get older.
okay. So yes, tube alloy or tubaloi does show up. It seemed to have gotten coined in England. In fact, was the name
Yes.
coined for the British atomic project. And I remember reading somewhere recently. Of course, now I've forgotten where. Oh, it was the Quebec Agreement document between Roosevelt and Churchill about nuclear cooperation. And initially the document on the American side got misfiled because an aide to President Roosevelt thought that tube alloy had something to do with boilers for naval vessels. and so it got totally misclassified, misfiled from what it should have been. So yeah, tubaloi turns up, and some of the British along that line, some of the more outstanding British scientists that ended up at Los Alamos and in Canada get some entries, because those guys made some really significant contributions to what was going on. So if anybody has anything they'd like to try, let me know. The Belgian mining firm of Union Miniere shows up because of their contribution of uranium ore.
So I'm glad to see Edgar there. I can never properly pronounce his last name. Sergey, is that close?
Sengier.
Oh, is it? Okay.
It was kind of Belgian / French.
Okay.
He shows up in a photograph a little later on. I thought I had a photo of him. Let go. Oh, wait, let me go back. I thought I had a photo. Oh, there he is. Okay.
There you go.
Getting the Medal of Merit from General Groves on the left here. One thing I've been
46. Huh.
Yeah. One thing I've been trying to track down, somebody brought to my attention that in the December 1953 edition of Reader's Digest, there is a brief article about Sengier and his contributions to the Manhattan Project, but none of our libraries around here seem to go back that far. And so he's one of those characters, of course, one of those people that played such a role in this story, but is probably largely unknown to many people, and had the foresight to ship all of this ore, or uranium ore, from the Congo to the US before the Germans could get their hands on it after invading Belgium.
That
And
you're right. He did that for what, some 2 years. And
yes,
you might, I don't know if you've noted or not, well, you do, these ores were extraordinarily rich with
oh
some
yes,
containing as much as 65% uranium. That's good because, what's being averaged, well, you've got it here. What's been mined today is about 1%.
it was astoundingly rich
Yeah.
ore, and so a lot of that ended up right in your neighborhood, and in Hanford, of course. Excuse
Right.
me. So I've tried to get some of the more. I'm sure somebody could always criticize me. I'm sure that, well, if you included this person, why didn't you include that person? And so there was just there's some subjectivity to it. But I thought some of these more interesting but little less well-known people I wanted to highlight as well. Um, and people like Alexander Sachs, who took the letter signed by Einstein in the summer of 1939, took it to Roosevelt and briefed him on it. And though he was an economic advisor to Roosevelt, he had a pretty substantial science background as well, and really recognized the significance of this. And I think there was no equivalent of somebody like Sachs
Hmm.
in Germany who had access to the highest levels and recognized that this could really be significant. This is something that needed to be paid attention to. And I think there's one could debate this over a drink for a long time, the Allied versus German program, but there was really no equivalent of a General Groves or Vannevar Bush or an Alexander Sachs on the German side. And so I think aside from other issues they had of personality conflicts, they didn't have it just never got organized at the level that it did in the US. And for a physicist, sorry, go ahead.
I had opportunity a few weeks ago, months now, to bring General Groves' grandson, Dick Groves, to Oak Ridge, and he is working on a 13 episode documentary of the Manhattan Project. And he is digging out a lot of really good information. One is that Alexander Sachs wrote a cover note for the Szilard signed by Einstein letter, and just had basically a paragraph that summarizes an executive summary. And Dick tells me that the way that he has learned that during that conversation, President Roosevelt never actually read the letter.
No, probably not.
Only read the executive summary and said, what you're trying to tell me is that Germany's going to drop a big bomb on us and we need to get to it first.
Yeah, that's right.
And
I thought, sorry, go ahead.
oh no, that's the end of it.
Yeah, I thought I had in here, buried somewhere. Oh, okay. I thought I had a link to Sachs's cover letter, but maybe I've deluded myself.
I know now that'd be good if you could find that. And
Yeah,
also I noted that you mentioned a report that Sachs wrote, an unpublished report.
I'm just making a note here.
Yeah.
That report is remarkable. Just making a note. Okay. It it's not readily available. So
Hey, your first sentence there says valuable resource of
oh yeah. Okay. Some years ago, I'd read a reference to that in Rhodes's book,
okay.
and I thought this was several years ago now, and I thought, wow, I wonder, like, who has a copy of this? And I remember I spent better part of an afternoon just noodling around on the web trying to track down if anybody had a copy of this, and so I was a couple of dozen links deep, and it turned out that the University of Melbourne in Australia had a partial copy in
My
their rare book library,
God.
and I got in contact with them, and they responded very promptly, and scanned me a copy and of what they had,
Yeah.
and sent it to me. And so there probably not many copies of this thing floating around, and I doubt I could recreate now how I found that link.
Uh,
But it turned out to be one of those things where you spend a couple of hours seemingly pointlessly on the web, and then you hit pay dirt. And, you know, and his anticipation of things in this sort of personal report was remarkable. He was anticipating nuclear powered aircraft carriers and submarines that could have essentially unlimited range,
wow.
that could carry nuclear weapons, and just how this could um, uh, totally upend some of the existing strategic concepts
The
in the
timing
world.
on that is interesting. August of 45.
Yeah, it's just incredible. And some of these people were just so far ahead of their time in their thinking. Um,
Hmm.
was really surprising. And yeah, I'm glad you mentioned Dick Groves, because I know him. I met him. I know he's working on this thing, and occasionally I'll get something from him where he wants me to check the physics on it, and he's got a database of sources on his
Oh, he
computer
does.
that's
Yes.
just it's just overwhelming. It must be hundreds and hundreds of things, and he's using some database program that cross-links all this stuff.
Yeah.
And his, I don't know if you've seen a draft copy of his script,
I have not.
but some of the photographs he's dug up
Huh.
are just wow.
I
I
need, yeah, I need to ask him to share that with me. He will.
um,
He just hadn't thought of it, I'm sure.
my sort of secret, my private fear is that he's got such a monstrous thing built up. To present this to a prospective producer, I would think they would find it overwhelming. Um,
I'm afraid that's happened and he's having to do it himself.
yeah, because it's, it would just be overwhelming, and how then this would be kind of boiled back a bit into a documentary, I think would be a real challenge. But I know he's trying to track down people who can do that sort of thing. I really hope he makes it work. There is links, see if I can find an example. Links not only to photographs, but occasionally to documents. I'm just looking to see if I can find an example. Documents are, say, I don't know what's going to happen. I'm not going to do this, okay? But because I don't want to screw this up. But there will be sometimes links to documents, other references, particularly government documents and National Academy of Sciences biographies of people and that sort of thing that will be hot linked as well. So it kind of goes on down, and the very last entry Very last entry. Oh, here we are at Y12.
Oh, yeah,
how
spend
can I
there, yeah.
talk to you folks and not mention Y12? So the electromagnetic isotope enrichment complex at the Clinton Engineer Works, which has its own separate entry, kind of overall entry that links to these other particular things like X10 and S50 and K25. And so I even have a table of when your various alpha and beta
Yes.
facilities came online. And I still remember, Ray, when I visited there and you were showing me the alpha Calutron pilot plant building.
You have a typo that you need to
Oops.
correct. The last entry in the columns, 9204-3, should
Yeah.
be 9204-4.
Horrors.
Well, if nothing else, we caught that.
Oh, drat. Okay. God, that shows you how you can look at something a dozen times
You
and
can't,
never see it.
yeah.
46.
And I'll point out to the folks who on the class here, most people don't realize that beta 4, 9204-4, did not get started until November of 45. Okay.
After the,
After the war is over.
yeah. That's right. Things did not just shut down.
Not until December of 1946 is
Yeah.
when the decision was made to move to gaseous diffusion only and eliminate the Calutron process, with the exception of beta 3, 9204-3, and building 9731. Both of those continued to operate beta 3 until 1998 and 9731 until 1974. And what they were doing was separating all of the stable isotopes that were some sent over to the graphite reactor. We had a question in the chat.
I was just looking at it about the dates.
Are the dates correct on the chart? And I'll confirm that those dates are accurate. I have the same chart, and I pulled those dates out of the Tennessee Eastman archives when I was still at Y12. So I am comfortable with the dates.
Somebody else. Yeah, the last one.
Yeah.
I see that. Yeah, that's right. It's and there was an addition to the K25 plant that didn't come online until after the war as well. The K27, and then there was others, I think, after that. So there was an answer to the question, these facilities kept expanding after the war.
Yeah.
And more reactors were built out at Hanford to synthesize plutonium. So things just didn't shut down on August 6th. No, pardon me, August 14th. I was going to say something and I forgot. Maybe if I think of it, I'll mention it. So it's yeah, I've tried to get a fair amount of detail in here, and it's kind of fascinating to come across some of these. And it's a testament to me, how long you mentioned some of these things kept operating, and some of the Hanford reactors operated into the 1960s. And I think that's a testament to how well they were built in 1944. That's remarkable. And in the case of Hanford, the reactors were still operating, but they'd been superseded at that time by much bigger ones. It wasn't that they were still operating. It wasn't that they were not operating. So as we get to the end, the very last entry is an obscure facility called the ZEEP.
Hmm.
which was the first reactor outside of the United States to go critical. And the Manhattan Project had a fairly active reactor theory and development group in Montreal, and had a couple hundred physicists and chemists and engineers working there. And they developed a heavy water moderated reactor that had used heavy water isolated in both the US and Canada, and went critical on I don't have, my God.
You need to add the date.
I need to add that, which was, I know by heart, was September 5th, 1945.
It says it remained in operation until April 1947, but nowhere do you say where it went critical.
Oh, okay. Well, that will get corrected. Okay. And that is a bit of history here. There was a heavy water pile in the US, the CP3 pile in Chicago, which came online, I think, about 1943 or so. And 1944, pardon me. Okay. And so ZEEP wasn't the first heavy water pile, but was the first pile outside the U.S. And that group in Montreal was kind of the genesis of Canadian reactor technology, and reactors in Canada use heavy water moderation and unenriched uranium. So that the process of uranium enrichment, of course, was never really developed here. So the reactor development took this different tack of unenriched uranium, but with heavy water moderation. And if you've heard the term CANDU, C-A-N-D-U, Canadian Deuterium Uranium was the acronym for this whole series of reactors. And you can blame the Canadians for the Indians getting a bomb, because back in about 1970, we sold a CANDU to the Indians, and they were extracting plutonium from it. So there's some interesting connections in the, I guess you could say, the way the nuclear proliferation worked. I see there's another chat.
Yeah, what is heavy water?
Okay. Okay, a chemistry lesson.
Yes.
The ordinary water, like you would have in your coffee, the hydrogen atoms are a single proton in one orbiting electron. But there's a variant form of hydrogen called deuterium, which consists of that proton bonded to a neutron. And so it's literally is heavier. And it was discovered, isolated first about 1932. It occurs naturally. And the advantage of this, it has no chemical effect. The neutron doesn't affect the chemistry of the water. So you could drink it just like ordinary water. The advantage in the nuclear business is that if you're trying to use water as a moderator and a coolant in a reactor, the hydrogen will absorb or capture, let's say, the ordinary hydrogen atoms will capture some of the neutrons, because this heavy water is stable. And so that will depress your reactivity somewhat. And it turns out you can't make a reactor with ordinary water and unenriched uranium, because that effect is just enough to suppress the reaction. But if you have this heavy water, the neutron's already there to start with, so the hydrogen doesn't capture any more, and it doesn't have this kind of deprecating effect on the reactor. And so there's that different and that means you can get away without the huge expensive Oak Ridge technology of enriching uranium. So I hope that made some sense.
So, Sue, does that help you to understand heavy water?
Yes, it does. And I am just wondering, that last part of my question is, how does water become heavy?
I think the answer there is astronomical. It was formed in whenever water. Okay, I have to back up here a minute. In whatever local supernova gave rise to our solar system, when some sun exploded billions of years ago and seeded this local part of the galaxy with the elements that became us, uh, hydrogen atoms in a star would naturally pick up neutrons in that supernova explosion. So it really is primordial. It's there from the sort of origins of the galaxy, and it's apparently stable forever.
So
Uh,
how is it created in a heavy water plant? How do we
oh,
create?
so it exists in ordinary water, um, and so it's just a natural um, uh, component of ordinary water. I forget the percentage. It's pretty small, like a percent or two, but it can be isolated from ordinary water by some kind of a distillation method because it ends up having a slightly different boiling point than ordinary H2O. And I know that here in Canada, there's a huge distillation plant on the Ontario side of Lake Huron that just extracts tons of water from Lake Huron and distills out the heavy water for use in these reactors. And so it's a naturally occurring. I imagine that every time you have a cup of coffee, you're getting a wee bit of heavy water.
Okay, so it's just a matter of separating that hydrogen atom with an extra neutron because it has a different boiling point. That means you can distill it
Yeah.
and collect it.
The,
Thank you,
the,
Sue. That was a really good question.
the neutron is everything
Yeah,
in the Manhattan Project. I mean, you might think that the difference between uranium-235 and 238 is 3 neutrons. What difference would that make? But it makes all the difference.
yeah,
And it's amazing to me how if just a few things in nature had been a little different from what they are, or if a reaction cross section or density had been a little different of some material or something, a spontaneous fission rate, the whole thing might not have existed.
that's very true.
So anyway, I know I drone on here.
That's good.
My my wife's heard this a zillion times. So there's a bibliography linked to all the various entries, and I'll scroll through that quick. And then there's a very brief chapter 3, which gives
I'm always,
uh, kind of a pretty condensed chronology that covers some of the basic discoveries in nuclear physics. And then when we get up to the wartime era, of course, it becomes a little more dense. And of course, a lot of these things are referred to in the various encyclopedia entries. A thing that's stunning to me is
hmm,
how so many things were happening in parallel in various places that eventually sort of came together. And for example, okay, um, right around early 1940, February leap year, there was a group, a collaboration between some people at the University of Minnesota and Columbia University in New York, where they isolated a very microscopic sample of uranium-235 to verify some of these fission theories that had been developed by people like Niels Bohr. So the ideas were there of, okay, this is the isotope that might be explosive. We have to test this. And that was published openly on March 15th of that year. And that's just a few days before in England, something called the Frisch-Peebles Memorandum, where two refugee physicists, totally unassociated with this work in America, had written a memorandum that detailed the possibilities of nuclear weapons. And they were probably aware this work was going on, but it hadn't been published yet. And their memorandum, so within days of these events, within days of each other, their memorandum goes to a British government official who realizes the importance of this and sets up something that came to be called the Maud Committee to look into the possibility of a nuclear weapon. And there's these, you see these things in the chronology where events that are physically far apart from each other but related are just happening simultaneously, and people having the same ideas in different places at about the same time. And it's just kind of, some of the coincidences are sort of striking. So the chronology then gets a little denser as we move into the Manhattan Engineer District getting established in the summer of 1942, and goes down through the end of the war. In the last entry being the criticality accident at Los Alamos, where somebody was accidentally exposed to, I'm trying to remember if that was depicted in the Oppenheimer movie.
No, it
no.
stops before that. And it's, well, it doesn't really stop before that, but the Manhattan Project portion of it
I
does.
have an entry on that, and I don't know if how many of your class are familiar with this. I think I have a photograph. Oops. Okay. The Demon Core. Okay.
It caused at least 2 deaths. Yeah.
Yeah. So I don't know how many of you have heard of this, but there was 2 accidents at Los Alamos where people were exposed to basically a briefly critical core of a nuclear weapon. In August 1945, when a fellow named Harry Daghlian was working with a plutonium sphere, which, so think of something about the size of a softball or baseball. And the sphere itself was not quite big enough to be critical mass, but they would use blocks of a tampering material that could reflect neutrons, escaping neutrons back in to the core. And they would do these tests. They called it tickling the dragon's tail, to approach but not quite get to criticality, to check their theories of critical mass. And he one of these blocks slipped out of his hand and caused a brief chain reaction. And so he's basically standing right there and got a lethal dose of radiation. And then a few months later, in 1946, and you sometimes see this depicted in movie depictions. I thought I had a, there we are. Okay. I hope I made that bigger.
You did.
Okay. So this is a recreation And what you have here is this fellow holding in his left hand this hemisphere of a tampering material. And underneath that, hidden underneath that, would be the sphere of plutonium about baseball size. And he's holding the tamper material just slightly cracked open with a screwdriver. And the premise was that by twisting the screwdriver, he could almost but not quite fully lower the tamper hemisphere onto the sphere of plutonium, which he didn't want to do. You imagine people actually doing this, because if it closed fully, it would reflect back enough neutrons to have a brief chain reaction. And that's what happened. The screwdriver slipped, and he got a brief chain reaction and had to knock the tamper hemisphere off with his hands. And so that was called the Slotin accident. But that put an end to all hands-on criticality work at Los Alamos. After that, they did it by remote control behind shielded, in shielded chambers. So there was they got away with things, I guess, that would never be allowed now. Another experiment that they did in this photograph below was something called the Dragon machine. And this would drop. You see, it's fairly tall. There's a chair down here for scale. This would drop down a guide wire, a slug of uranium-235, and it would pass through. It would pass through a plate of the same material, and the passage would just be brief enough to create a chain reaction as the slug passed through for maybe a few milliseconds. And they could make measurements of the reactivity rates and neutrons released and heating effects and all this sort of thing. So it had to be very, they did a lot of practice shots with this before they used, honest to God, uranium-235, because they didn't want the slug hanging up in the middle of the plate. But this is the sort of very literally hands-on experiments that these guys were getting away with.
Okay, Cameron, thank you very much for a good presentation. Any other questions any of the class has of Cameron? Before we wrap this part up, we've got just a few minutes to talk about our next upcoming session. Any other questions for Cameron? Either in the chat or just unmute yourself.
Thank you for bearing with this.
Yeah.
As Ray knows, I'm always happy to talk about the Manhattan Project.
I appreciate that, and I will get you some final comments by next week. And
I would like to make a comment about how astounded I am always to be with so many ultimately intelligent people. I don't understand enough to even ask a question, but I sure admire all of you guys.
Well, it's
we fooled her.
Oh, wow.
Thank you. I'll take that as a compliment.
Well, yes, ultimate.
Sometimes I get a remark like that from my students, and the analogy that I like to use is I say to them, well, how do you get good at playing a sport or a musical instrument?
Yeah.
Or language? And it's practice, right? And it's just years of obsessive practice, I guess.
Well,
and,
kudos to you.
And
stop your share, if you will, Cameron.
Sorry, say that again.
Stop the share. Stop sharing your screen.
Oh, stop sharing. Okay. Stop share. There we go. There we go.
And
okay.
What I want to do, very good. What I want to do is to ask if we have ideas for the next class of yet even more stories from the Secret City. It'll be coming out in the fall. And if you don't have anything to input right now, you can send me something on email to draysmith@comcast.net or send me a text 865-660-9527. And this class will be posted up on YouTube. I'll send you a link, and then I look forward to having you join me again in the fall. Any input? All right. Well, I will see if I can get some of Dick Grove's time and see if he will, maybe by then he will have gotten far enough along on his project that he can at least give us a review of it. And I'll remind you that the book that Lee Rettinger and a writing team, of which I was one of the co-authors, has produced about the relationship between the University of Tennessee and Oak Ridge over the years. That book is being released next month.
Oh, I ordered a copy, but it hadn't shown up yet.
Well, no, you got it on a pre-order, so it'll
Okay.
leave in July. And we're going to have some book launches in Knoxville and also a couple in Oak Ridge. We're going to try to do it at the library and also at the American Museum of Science and Energy. So be looking for that announcement in local media. And of course, I'll be putting information about it on Facebook. All right. If there's nothing else, thank you all for being with us. And thank you, Cameron, especially for an excellent review of your book, Encyclopedia Manhattan Project.
Thank
Thanks
you
very-
so much.
Thank you. Thank you.
Thanks.